Hello everyone, welcome to this talk. This talk is titled, What's New in Shader Graph Ready for Production? So I'm going to show you a few things that are new to Shader Graph, and I'm going to show you a couple of tips as well. First, who am I? I'm Ciro Continisio. I'm lead evangelist for the EMEA region. My focus is on games, and I like to talk about Unity, but showcasing like a bit more advanced uses of Unity in general. In the past, I was a developer of my own games, and I worked as a tester at TA. So, Shader Graph. It's a tool, I'm pretty sure you know what it is, right? But like, just to recap, it's a tool that's available as part of the SRPs, so the scriptable rendering pipelines, meaning that, no, Shader Graph is not coming to the built-in pipeline. But it is available as part of universal render pipeline, which was called Lightweight, and HD render pipeline. It's a visual shader editor, node-based, and the cool thing about it is that it gives you instant feedback because each node has a preview. So as you build your graph, you see how your shader is being manipulated in time in the graph. We used it in several of our own demos. Of course, some game developers are using it as well. You've seen it probably in FPS Sample or The Heretic. Not everything is done in shader graph. Some of the things are like shaders that come out of HDRP out of the box, but to create some effects here and there. For example, in the FPS sample, it's used to like make the plant sway a little bit. Shader graph can also be used to create interesting effects. Myself, I've used it a lot to do that actually. So I've made a few experiments here and there, like this character that you might recognize from a Nintendo game. The ball that you see, the refraction that it creates, is all done in shader graph. And it's actually only one surface. It's not like double-sided. There's a few tricks to it. I created this shader here where I swapped the shadows with a watercolor texture. I used it to make a small mobile game where I made like a custom toon shader, very simple one. For mobile games, toon shaders can be a great trick to squeeze as much performance as you can while still having an interesting and pretty readable action on a small screen. And this is another shader, also a toon shader, but a bit more complex, that I made still with shader graph, simulating like the style of Zelda Breath of the Wild. I'm going to talk about this tomorrow in another talk. Yeah, this is a close-up or a still. So the good news is shader graph came out of preview in 2019.1. When I say came out of preview, what do I mean? Verified package, right? What does this mean in practice? It means a few things. First, it means that it's ready for production. So we're actually suggesting that you start using it in your own games that are in production and not just pre-production. It means that your graphs will be upgradable. So when we say the package is verified, we're saying that if you produce something with that package, we want to make sure that that something will upgrade throughout versions, which is not really guaranteed for a package that is in preview. So if it is in preview, we still reserve the right to break your data, basically. But if it's verified, we want it to be preserved. And the other cool thing is LTS, so long-term support versions of Unity, the one that comes out at the end of the year. If the package is verified by that time, it falls into the LTS version, and it means that for 2 years from that moment, we will backport all of the critical high user pain high user pain bug fixes to that version. So shader graph will be basically all the high user pain bug fixes that we will see in 2 years will be backported to the LTS of this year. So moving on to like the general improvements that we've seen coming to shader graph as it was released. First thing to mention is we now have more master nodes. It started only with PBR and unlit, but already in the universal rendering pipeline, now you have 4 master nodes. The master node is the node that is basically the endpoint of your shader. It's basically the one that contains like the template of the shader, which is going to be filled with the data that you create in the graph. So now Universal Render Pipeline features these 4 master nodes, unlit, PBR, and then for 2D, if you're using the 2D renderer, sprite unlit and sprite lit. The high-definition render pipeline features 6 nodes, master nodes, lit and unlit, of course, but also some nodes that you've probably seen in the Heretic, so the ones to create fabric, to create hair, and then also the one that supports decals, and another one that is called stacklit, which it's a special shader only available in HDRP, which is basically 3 shaders in one, if you want. It's a shader that is made, 3 materials in one. So it's like 3 materials layered, and then through some masks, you decide which part to uncover and which not, which is really useful for example, creating the coat of a car, where you have some base of metal, then you have some imperfections on top, and then maybe you have a layer of painting. So the stacklit master node allows you to harness all of that into shader graph. And then in the future, we're going to have some more master nodes, one for the UI, one for post effects, so full screen post effects, and one for VFX graph, visual effect graph. One of the first improvements that I want to mention is the precision. Precision is a small drop-down that you will see on many places. You have it on the node level, so per node. You have it on the graph level or on subgraphs. And basically, it's a small drop-down. As you can see, it says inherit, float, or half. So it's allowing you to choose the precision of the calculations of your shader graph, meaning that you can now create shaders that are targeted to desktop devices or to mobile devices, and you can choose that precision. And you can choose that precision throughout the graph, so you can do it for the whole thing, or you can do it only for some parts. Maybe that calculation is not really, precision is not really important in that part, and so you can decide to switch down to half. So yeah. Another improvement was the color mode. So color mode is these colored bars that you see for each node. And as you can see top right in this image, you're able to choose the color mode from 3 different types. It can be used to categorize nodes. So nodes are automatically colored based on their category, and a different color is displayed. It can be used for visualizing the precision of your nodes, because you can do the precision per node, so it's useful to, at a glance, see where your node, where your graph is on a different precision, half or float. Or it can be used for user-defined colors. This is really useful if you have a convention in your team, and maybe you assign a specific color to a specific type of node or a specific subgraph that you're reusing in different shaders, then you can instantly recognize that node even if the graph is zoomed out. And you can move between these modes and visualize all of the 3 things wherever you need them. Another thing we brought to shader graph, which has a big impact, is extending the functionality of subgraphs. So subgraphs, in case you don't know, are basically, they are parts of a graph that are encapsulated and taken into another asset. And so once you do that, you can reuse these assets all over your graphs, even multiple times in the same graph. And yeah, their use is multiple. As I wrote here, obviously reusability. So if you have a certain piece of functionality that you're reusing over and over again in your graph or in multiple graphs, it's great to make it into a subgraph. The other use, of course, is to declutter graphs. So the ability to remove some of the complexity and hide it inside one node. And then the third thing is obviously better team workflows, because since they're different assets, people are able to work on subgraphs individually from the shader graphs that they're contained into. It's kind of like the concept of nesting prefabs, if you want. So you can now spread the work across multiple team members, and there's no conflicts. So one of the improvements that we brought to subgraphs is the improvements to the outputs. In subgraphs, you have this final node, I guess it's called output node, which looks a little bit like a master node, right? It's the end part of your graph. And once you click on the cog, you get this drop-down that allows you to define the outputs. So one of the improvements was to make these outputs nameable, so now you can rename them, which means that whenever you use this subgraph in a shader graph, you're going to see these properties as named, and you know what they mean. They can be reordered. And now they support all types. Before we were simplifying it and coming out all as a vector 4, but now you can actually support, like you can put the outputs in all of the types that are supported by shaded graph. The other cool thing is that subgraphs can now be nested and indefinitely, meaning that up to a certain limit, but you can go deeper and deeper and nest small chunks of functionality into bigger graphs and then into bigger subgraphs until you get to the final shaded graph. And one of the things that I want to show you live in the editor revolves around this. We obviously automatically check to prevent recursiveness, so we prevent you from putting the same subgraph into itself for a subgraph that is nested deeper into the parent or something like that. And yeah, there are obviously a fundamental capability in big projects where shaders can become very complex. And with the improvements that we did to subgraphs, we were able to unlock kind of like a new extra perk, if you want. So this is something that had been requested a lot by everyone since the beginning when shaded graph first came out, and it's the ability to add custom HLSL code to your shaded graph. In the beginning, we unveiled this API in C# that was called code function node. So it was a set of API revolving around a specific class that allowed you to declare a new node, a new type of node in C#. So you would create the class, and that would contain both the node definition, the outputs, and the HLSL code. And I want to point to this because this thing has now been deprecated. It was part of the preview. It got introduced around GDC 2018 through this blog post that you see here, and it got mixed feedback. So we decided to deprecate it and to move on to a different thing. The reason I want to point it out is because sometimes, as it happens with Unity, people produce a lot of content, and you will see this content floating around on the internet, and you might get confused. So if you see the code function node API and tutorials around it, they're not valid anymore. So the solution we found, we settled on was this custom function node. So custom function node is not a custom node that you make yourself, but it's a pre-made node that accepts a custom function. So as you can see, the interface looks very similar to subgraphs. And that's why I said, in improving subgraphs, we actually open the way to the custom function node. So the custom function node replaces the public C# API. As I said before, that's no more. No, don't look that way. It supports custom HLSL, both inside the node, as you can see here in this image. So you see here in this little box, you see sum equals A plus B. Sum is obviously one of the outputs, as you can see here. And A and B are two of the inputs. And you can barely see here, like A and B are here as input ports, while sum is currently covered. But anyway, this is HLSL inside the node, and then the other way is from an external HLSL file. So you can switch here string to file, I think, and then it allows you to connect an external text file in the .hLSL format, which can then be used kind of like as a repository of your custom functions. And then you can reference them from here just by typing in here the correct function name. And then this node will call that function and pass the inputs and receive the outputs. And then you can use it in your graph. The custom function node also makes it easier for us to upgrade a graph, because as we work around the functionality around the node, we can actually upgrade that. We can work on all that is surrounding it without breaking your graph. While before, with the C# API, we needed to, because it was using reflection and stuff, we needed to write something that was a bit more smarter, and the potential for breaking your custom nodes was higher. While with this one, if you were to upgrade the graph, you will only need to make sure that the HLSL is still working. But again, also as both Universal Render Pipeline and HDRP came out of preview, you can also be a bit more sure that your HLSL will still work. As part of this whole work around the nodes and custom function, we also added better error handling. So whenever a graph doesn't compile for some reason, especially if you're adding some custom HLSL code that doesn't work, you actually see the error inside the graph itself. And the error is the one that your compiler will spit out in your IDE. And also, we added a bunch of useful tips. So the one that you see at the bottom is there to like support you and make you understand what's going wrong in the graph. Another improvement is sticky notes and groups. So we added sticky notes to obviously give you the ability to annotate your graph. As you can see, there's like 3 different text sizes, and it has a light and a dark theme. And then we added groups, and groups are really useful. You see them here. So here I just grouped like these 2 objects, which might seem like a bit overkill. But actually, this is really good because groups usually have like a very big title. So even if you zoom out, they can be readable. And that's useful even if sometimes it can happen that you group just one node, just for that functionality of being able to add like a little big title on it. Yeah, so titles can be used to provide context because as you work in a team, not necessarily other people will understand what were you doing there. And also it's useful for moving and deleting nodes in a group in bulk. This is probably something that you didn't know, I hope, because it's really, really new. This one came out in shader graph 7.1.1, so the one that's compatible with Unity 19.3. It's a pretty recent addition. Keywords are basically a special kind of variable. They might look on the surface as like a Boolean, a regular Boolean that you can add to your graph. But the thing is, they allow you to create kind of like branches in your graph that are more powerful than the regular branch. You already have a branching node. But the thing behind the branching node is so because shaders don't really take if statements really well. So the branch node that we have in shader graph is actually not a real if statement, but it's a math operation. So it's taking 2 numbers, and then depending on a Boolean, it's actually multiplying one of them by 0 and one of them by 1. So the result of this is that even if you have a branch in your graph, you're still evaluating both sides, which for small shaders, for small shader graphs, is okay. Like it's a couple of addition and subtractions and multiplications. But if the shader is really, really big and you have a big branching path, that's really not okay because you're calculating both branches for each and every shader, even though you're actually using only one of them. So keywords provide you that functionality. There's different types. As you can see here, there's Boolean or enum. They can be local or global to the graph. And then there's different types. There's shader feature, multi-compile, or predefined. And then, for example, multi-compile is one that means that Unity will, when you build a game, compile different versions of that shader. And then depending on whether the Boolean or the enum is a certain value or not, it will use that version of the other version. So basically, it's kind of like eliminating the whole branch from your shader manually. But you don't have to do that work. So keywords are really useful. The other one that's really interesting is the ability to use, to define one keyword. You can only do one per shader. That's called material quality. It's this option here that's grayed out because I already defined it. And as you can see here, material quality is kind of a special keyword which you don't yet define yourself. So you don't feed it yourself to the graph, but it's the pipeline. So some kind of setting that comes from your rendering pipeline will give each and every shader this keyword, will make available this keyword on high, medium, and low values. And then in your graph, you can create a branching path. So basically, you can have a graph that adapts to the level of detail or the custom effects that you want to do, depending on what the level of quality is. This level of quality, as I said, is usually set by the pipeline, and you can expose it to the user, so the users can potentially like switch level of quality globally for your game, and then your shaders will react accordingly. oops, this is the final slide. So I want to jump into a small demo, because I still have plenty of time, showing you some of the improvements that I just talked about, but also, as I said, like giving you a few tips. So this very, very simple scene contains some assets from the 3D game kit, our friend here, Ellen, and then this crate that I want to focus on. So this crate, and I should have really been on this. Yes. So this crate initially, as you can see, it has just a regular universal render pipeline lit shader. So this is universal render pipeline, right? Is the renaming of lightweight render pipeline. And it's using one of the regular shaders from it. So this is what was called standard. So all the classic inputs, as you can see, metallic workflow, opaque, and then it has all of the textures and some colors and some floats. Now, the first thing I want to point you to is I have made a custom shader, and I can actually jump into this shader, so shader graphs, base material, and I remade the shader to look like the lit shader and to take the same inputs so that whenever I switch to it, I don't lose anything. Of course, the inspector looks different because it's not customized. It's just like literally shooting out all of the properties one by one. But the cool thing you can see is I don't need to reassign each texture and each color, which is quite good as you're migrating a project, or maybe you have a project that's full of normal shaders and you want to swap a few objects. It's really good to make your custom shaders with this in mind. So how do you do that? It's very simple. You really just need to make sure that the properties of the shaders are named in the same way. How do you find about that? You just go to, for example, the lit shader, right? I have it here. And you go to the cog, select shader. Unity is going to select the shader in the rendering pipeline, because remember that universal rendering pipeline, like all packages, is here, is available to you, and you can look into that. So I have now selected the lit shader, and here you have the other ones. And then in the inspector, I just need to take a look at the property names. The property names are always the ones that start with an underscore. So if you make sure to respect that naming convention, once you switch shader, all of your maps and all of your floats and all of your colors will be preserved, which is quite helpful for if you're migrating a project or if you plan to. So I respected that, so I can just switch the shader. I do it here. Shader graphs, base material. And now I have my stuff in here, and I can keep working on it, and I can define, well, metallic is not plugged, of course. But I can, like, do stuff like this, right? So in constructing this shader, I did this. I started with, well, I want to show you the final result first, and it's this one. So I kind of like created a gigantic, thank you, Unity, please show the UI correctly. I created a gigantic subgraph that takes all of the inputs of the standard shader, of the lit shader, and just sends them out to the PBR master. So I'm using a PBR master node to obtain the same functionality as the lit shader, and here I have all the inputs. And then in the blackboard, I defined all of the textures and all of the floats, and the trick that I told you before is here. You see underscore base map, underscore base color. So I'm respecting the same naming convention as the lit shader, which means that I can always switch between them. So this is the blackboard for my main shader. And then this one, as I said, is a subgraph. So if I dig into this, you see that here I have, again, an output, which is the same kind of stuff that I expected. And if I go to the blackboard, again, I still see like most of the properties that I saw before. So what this subgraph is doing is a container for some other subgraphs. And it's this one, sampler texture. And I want to dig into it just 1 second. Then I will explain it. So this is my baseline, is my deeper level of subgraphs. This one is a subgraph that provides very, very simple functionality. As you can see, the blackboard is texture 2D, tint, and tiling and offset. So this one is taking a texture. here, sampling it, using the tiling provided by tiling and offset, and potentially tinting it for a color. The color, of course, is white, so by default, so that if I don't provide a color, it's like it comes out untouched. And then, as you can see, I bring the alpha as it is to the combine node, and I bring everything to the output. So basically, I'm just sampling a texture. I also have a variation for this for the normal. So there's another subgraph that just reads a normal texture. You can see that it's a bit simpler because you usually don't tint normal textures. You don't have alpha, and yeah, and then the other difference is you want this type to be normal. But they're basically the same stuff. Then I use them all, whoops, this one. I use them all to build this one, this intermediate subgraph, where I have my albedo and tint, then I have my normal, then I have my emission, then I have my metallic and smoothness. And as you can see, all of them are using the sampler thing, the sampler subgraph that I created before. For metallic and smoothness, I'm modifying the input a little bit according to these two parameters, which are floats. And finally, occlusion. And the other interesting thing is here, as you can see, I'm doing the channel packing. So I don't know if you know, but there's a technique called channel packing, which means you have a texture, and in each channel of the texture, you encode a different property. So the texture is not used as RGB, but each channel, R, for example, in this case is, okay, the UI is bugging pretty bad. The R is taken to the metallicness, and the alpha is taken to the smoothness. And G and B are currently unused, but I can use them in the future. So by doing this, I bring them all to here, and then I exit in my base material, as I showed you before. Well, number one, this is a really good workflow because let's say that tomorrow your team says, you know what, we need to swap those channels. We need to pack our textures for metallicness and smoothness, and maybe we want to pack the occlusion as well into that. We want to put the occlusion into the blue channel. So if you use this subgraph in all of your materials, then you don't need to do anything to them. You just dive into the subgraph, and you make the change to this level. And then as you save the asset here, that change is propagated to all of the graphs that are using this subgraph. So it's a really good workflow for big teams. And the other thing I want to show you is this. Let's go back and take a look at the game. So if I need to do one thing first. So this destructible box, I will switch it to another shader. It's called interactive material. And I press play. And now I'm in play mode, and as you can see, I can make the crate disappear by pressing, I'm pressing a button, I'm pressing 1, and then I'm pressing 2, and I can make it shake. And these are two effects that I have applied to my shader graph, and I can also mix them together, so it can shake and appear and disappear. So what I'm doing here is I'm delegating to a shader a couple of effects that I could have done in different ways. I could have had a C# script to drive a property. So if you see the destructible box, there's a couple of properties. So you see all the inputs that I had before. And in addition to that, you have a bunch of properties here, like appear FX time and playing forward, shake FX time, and then 2 settings for the shake. So if I were to press the button, you see that the shake FX time here is changing. It's the time where the shake starts. So potentially you could, of course, you could like do this thing in, well, this is a bit hard to do in C#, but you could animate these things through an animator, especially this, right? The thing is, obviously, if you do it in shader graph, it's going to be much more performant because in Unity, and this is a general thing, most of the time your performance bottleneck is on the CPU. So the more work you can send to the GPU, the better. And so if I'm delegating this effect to the GPU completely, It's better for my performance. But it could be annoying to build a shader graph just for this, and then that shader graph is really, really specific to this use, and then tomorrow I need to make a new one, and I create a new one. So the smart thing to do with the workflow that I showed you before is to have something like this. I called it interactive material, and I built both effects, but as you can imagine, I can just unplug one of them to remove the functionality. So in this case, you see I have the PBR master, like before. Most of the inputs are coming in as they are. From the subgraph node that I showed you before, exactly the same. The inputs are all here, coming from the blackboard. So as I said before, this shader looks very similar to the lit one, which means that if I switch, I get all the properties. But then some of these, the outputs of the subgraph are basically passed through another section of the graph, which is still bugging. And in this, I build my functionality. And so my functionality is here. I have these two subgraphs. One is called timer 2 ways, and one is up here, timer 1 way. And basically, they provide this functionality where, for example, let's talk about timer 1 way first. I give it a start time. So I say, for example, in my game, I'm at second 16. And then the shader will say, OK, from 16 to 17, I play this effect, and calculates a number that goes from 0 to 1 and sends it out. And then in my master shader, this one, you see I pass the time, I run it through my subgraph that I just mentioned, and then I use that with a few math calculations to drive the position of the vertices. So that allows me to press the button and the crate will shake. This is very, very simple functionality. Timer 2 ways is a bit more complex because I wanted a timer that could go forward but also backwards. So I have two parameters, I think, which are start time and a Boolean playing forward. And playing forward is going to say calculate from 0 to 1 or from 1 to 0. So it reverses the effect. And again, I exit with a simple float. And then in my interactive material, I can, sorry, it's here at the bottom. So here's timer 2 ways. You see I pass Boolean and float, and I exit with a float. And that float, I use it through a noise. I use it to step the noise, so I make the hard edge. And that gives me transparency. And then as you can see here on the branch here at the top, I also use it, again, it's disappearing, I don't know why. I also use it to drive the emission. So just to show you the effect again. Timer 1 way, I give it a start time when I press the button, and it shakes for a second. Timer 2 ways, play forward and play backward. So start time and play forward, start time, play backward is false. And as I said, I can mix them because they're independent from each other. And just to reiterate the point, if at a second point in time in my production workflow, I would need to change how the basics of this shader works, I can just go here into the subgraph and do that. And all of my interactive materials will still work. Of course, in this demo, I kept these two effects as part of this main graph, but you can also make them subgraphs. So you could make the shaking effect a subgraph and reuse it in different subgraphs. You can make the appearing, disappearing effect, and and then build like a library of effects that are either 1 way or 2 ways, and then you can mix and match them in different graphs. So this is, in my opinion, a very powerful way of working, and also very future-proof for any potential change that your team might make to the graphic pipeline. I haven't used keywords in this graph. I should have. But as I said, because they arrived pretty late, I didn't. But basically, for example, here I could have, well, this is not a really great use for keywords, but I'll show you where they are. So if you go to the blackboard, you press plus, You see they're here. Boolean, enum, and material quality. So if I define a Boolean, it appears at the bottom of my blackboard here. And if I confirm, I can then use this Boolean as a branch. So you see it comes as a node where I can bring in 2 values, and then depending on what's the value of this keyword, Unity is going to compile 2 different versions of the graph. And this is it for the demo. So if you want to learn more about shader graph, don't forget we have Unity Learn Premium, which is a premium version of the Learn website. There's a few tutorials, interesting tutorials on shader graph. Learn Premium comes as free if you're a Plus or Pro user, but if you're not, with this code, you can get like 3 months for free. Unite CPH19. And if you want to learn more about shader graph, tomorrow I'm going to give another talk a bit more advanced. So if this was a bit basic, the other one will be a bit faster and more advanced. And I'm going to show you how I created this more complex toon shader. So starting from the custom HLSL, the custom function node, and how I put the different inputs together to create the final result. And it's tomorrow at 2, from 2 to 2:45. This is all from me. I don't know if there's questions. I can't see you. Thank you.